When dealing with crystalline materials, it often becomes necessary to specify a particular point within the unit cell, a crystallographic direction, or some crystallographic plane of atoms. So we need a way to identify directions and planes of atoms within a crystal structure. Well, why do we need to know the directions or planes, or why do we need to specify them? Well, there are many reasons. Just to name a few, first of all, we're going to learn the deformation of materials. So you will learn later deformation and loading occurs only on certain planes in certain directions. So before we can predict how materials fail, we need to know what modes of failure are more likely to occur and along which directions within which planes. And also, other properties of materials, including electrical conductivity, thermal conductivity, elastic modulus, can vary in a crystal with different orientations. The crystallographic directions and planes are described using three integers, which are referred to as Miller indices because it is introduced by the British mineralogist William Miller. And the basis for determining the indices or index values is the unit cell. So we are defining the directions and planes within one unit cell, and set up the right-handed coordinate system by locating the origin at one of the corners, usually at the back corner over here, and the x, y, z axes are coinciding with the unit cell edges. So if we have a regular unit cell, you will see the XYZ axis set up like this. But we will just focus on the cubic system. So for a cubic system, we know the x or the three edges are perpendicular to each other. Therefore, the x, y, z axes are mutually perpendicular. And also alpha, beta, and gamma angles are 90 degrees. Furthermore, the three edges of the cube are equal. So instead of having A, B, and C, we just use A for the edges of this cube. Sometimes it is necessary to specify a lattice position within a unit cell. Well, a lattice position actually is just a point. So we need to find the point coordinate in a unit cell, which is determined as fractional multiples of the cell edge length. So for a general unit cell, we have A, B, C as the edge length, but if you have a cubic cell, all the lengths will be A. So now let's take a look at one example to see how we find the lattice position or the point coordinate of this upper corner within the unit cell. So first of all, again, we need to set up the right-handed coordinate system. Usually, the origin is located back here at the back corner, and the x, y, z axes are along the three edges respectively, like this. First step is to find the lattice position based on this x, y, z axis. So to do that, we can do an imaginary path starting from the origin and then walk along only the XYZ axis or XYZ directions. So first I'm going to walk along the X direction, so the distance I traveled is A. And then I change my direction to walk along the Y direction, and the distance I traveled is B, the other the edge length of this edge parallel to the Y axis. And finally, I need to change my direction to walk along the Z direction or parallel to the Z axis. And the distance I traveled is C. Therefore, the X coordinate is A, the distance I traveled along the x direction, and the y coordinate is B, the direction traveled along the y direction, and the z coordinate is C. Therefore, the lattice position will be A, B, and C. Second, divide by the unit cell edge length respectively. So along the x direction, the edge length of this unit cell is A. Therefore, we have A divided by the edge length in that direction, which is A, and B divided by the edge length along the y direction, which is B as well, and the last coordinate C divided by the unit length. Actually, the edge length is the unit length in that direction of the unit cell, so it's C, and remove commas. Therefore, we have 1, 1, 1. So again, we are using 3 integers to representing the location of the point now. So here, the point coordinates for the unit cell corner are 1, 1, 1. Again, in materials engineering and science, when we writing those point coordinates or line, the crystallographic lines or planes, we do not put comma between those numbers. Okay, no comma, just 1, 1, 1. After figuring out how to find the lattice position or a point coordinate, let's move on to see how to find the crystallographic directions. Let's start with one example. We're looking for the direction indices for this given direction within the given unit cell, and the XYZ coordinates are already setting up for us. If it's not, so the first step will be to set up the XYZ coordinate. So basically, to find the direction indices is to find the XYZ components of the given vector. So if you learned how to find a vector, then you will know how to find this direction indices. Well, to find the direction indices, step 1 is to determine the coordinates of the vector tail. So the starting point of this vector is the tail of the vector. So usually the tail of the vector or the crystallographic direction starts from the origin like this. So now point 1 is the tail. The coordinates are 0, 0, and 0. And next, we're going to find the coordinates of the vector head, which is point 2 on this figure. So the head coordinates, again, we can use the imaginary path method to walk from the origin first along the x direction. So we traveled the length A. So the unit cell has the edge length of the unit cell along the x direction is A, along the y direction is B, along the c direction is C. So that's the convention. So now A along the x direction and y is 0 because we don't need to travel along the y direction, and the z direction is half of c. Therefore, this is the point coordinates of the head of this vector. So the next step is we're going to use the tail coordinates to subtract from the head coordinate, or the head subtract the tail, corresponding coordinates subtract the corresponding coordinates. So A subtract A, 0, 0 subtract 0, c over 2 subtract 0. And next step, so we did the 2 steps together, we're going to normalize the coordinate differences in terms of the lattice parameters A, B, and C. So divided by the first component divided by A, second component divided by B, third component divided by C. Again, A, B, C is or are the unit length of this unit cell along each direction respectively. Now, after performing this normalization, the first value becomes 1. The middle value, the y component, is 0, and the z component is 1 over 2. So that's the value now, after step 2 and step 3. Now, step 4 is to reduce to smallest integer values by multiplying each number by 2 to reduce this set of number to smallest integer values. Again, Miller indices include 3 integers, so fractional numbers are not allowed in the final result. Therefore, we need to reduce the numbers to smallest integer values. So 201 is what we have now. The last step is the format that we need to satisfy or we need to use. We're going to enclose indices in square brackets with no commas. So here is the final result. The Miller indices for this given crystallographic direction is 201, enclosed in square brackets. So whenever you see square brackets, that means it's for a line, a direction, not a plane or not a point. Let's take a look at another example to find Miller indices of this crystallographic direction shown here on this figure. So first of all, the XYZ coordinates are already built up, but let's also specify the edges, the length of each edge. So usually the length along the X direction is A, along the Y direction is B, and the length along the Z direction is C for a unit cell. So for this given direction, it extends from one unit cell all the way to another unit cell to the back. Okay, so now first step is to find the point coordinates of the tail and head of this vector. So point 1 is the tail, and we can use the imaginary path method to find the coordinates starting from the origin. First, we travel along the X direction, travel a distance of A. And then we change direction to walk along the Y direction. So this point is in the middle of the edge here. So the distance we travel along the Y axis or along the Y direction is half of B over here. And then we arrive at this point. Therefore, the Z coordinate is 0. So x1 is A, y1 is B over 2, and z1 is 0. And next, we use the similar method. We find the coordinates of the head, which is the point 2 here. So similarly, we're going to do the imaginary path starting from the origin. So first we walk along the X direction, but we are walking along the negative X direction by a distance of A because of the unit cell it's drawn here. And then we change the direction to walk along the Y direction. In the positive Y direction, the distance is again B, length B. And lastly, we change the direction to go along the Z-axis, and the distance we traveled is C to arrive at point 2. Therefore, the coordinates of point 2, x2 is negative A, y2 is B, and z2 is C. Next step 2, and also step 3, we can combine both steps. We're going to subtract the coordinates of the tail from the coordinates of the head. So x2 subtract x1, y2 subtract y1, and z2 subtract z1, and normalize by dividing by the corresponding unit length along the corresponding axis. So x component divided by a, y component divided by b, and z component divided by c. So here are the answers we have: -2, 1/2, and 1. So next step, step 4 and step 5, we can combine those two steps. We are going to multiply by 2 to eliminate the fraction, or to reduce the set of number to the smallest integers by multiplying by 2. So times 2, we have -4, 1, and 2. So this is the smallest integer group. And then we're going to place the set of number in square brackets and also remove the commas. So here, the difference between this problem and the last problem is we have a negative component here, or negative index here. So the convention for writing Miller indices for negative numbers is to write the over bar. Okay, instead of using negative sign before the number, we put a bar on top of this number to represent a negative index. So this is the result. For some crystal structures, several non-parallel directions with different indices are actually equivalent. So this means that the spacing of atoms along each direction is the same. So we call the groups of crystallographic equivalent directions as family of directions. Again, this equivalent means the spacing of atoms along each direction is the same. So let's take this 100 family of directions as an example. So assuming we have simple cubics. So this is the simple unit cell of a simple cubic. So we know that along the edges of the simple cube, the atoms are in touch. Therefore, if you choose any edge of this simple cube, the spacing of the atoms is 0, and they are equivalent. So this edge, for example, based on this coordinate system, the Miller indices is 0, 1, 0, parallel to the y-axis. So along this edge, the atom interatomic spacing is 0 because the atoms are in touch. And then along this 100 edge or direction, the atoms are also in touch. The atom atomic spacing or space of atoms is 0 as well. Then along this 0, 0 direction, the spacing of the atom is also 0. So we call those directions as family of directions. So this group of family or family of directions, the 100 family, actually including all the edges of a unit cell. So now you also probably figured out that we have negative ones. Okay, in some directions we have negative ones, in some directions or some directions we have the positive ones. We can say that in the cubic system, again, this only works for cubic system with 90-degree angles with the same edge lengths, which is A. So in cubic system, directions having the same indices regardless of order or sign are equivalent. In other words, as long as we have the three digits or three integers are the same, we have integer 1, 0, 0. We have 1, 0, 0. No matter which order do we place the three integers, 1, 0, 0, 0, 1, 0, 0, 0, 1. or no matter what sign we use for each integer. So we can have 1 or -1. And any combination means that's the same or equivalent direction. So another example can be, or more, this 100 is kind of special. If we have 1, 2, 3, for example, direction, and it's equivalent to 2, 1, 3, is also equivalent to -1, -2, 3, or -1, -2, -3. And there are many more, as long as we have a combination of 1, 2, 3, and a combination of positive and negative, and they are all a family of directions. Here are some common directions in a cubic or in a unit cell. First of all, the edge. Along the edge, we have 1, 0, 0. So this 1, 0, 0 with a square bracket indicating a single direction. So this specific direction colored in green. If we want to indicate all the edge directions, we can use a family notation. So this is the 1, 0, 0 family. The next one is the face diagonal. Again, this particular specific face diagonal, we use this square bracket to indicate a line direction or Miller indices for a direction. But if we want to represent all the face diagonals, we can use this family of directions. So this is the family, or this is the 1, 1, 0 family. So 1, 1, 0 family representing all the face diagonals in a unit cell. And same idea for the body diagonal. So for this body diagonal, it has the Miller indices of 1, 1, 1, or is the 1, 1, 1 direction. So to representing all the body diagonals within one unit cell, we can use the family of directions notation. So this is, or the body diagonal is the 1, 1, 1 family. Here are some notes on crystallographic directions. First, the crystallographic directions are vectors. So vectors has magnitude and a direction. So a direction and is negative are not identical. So we have been talking about 1, 0, 0 and -1, 0, 0. They are family of directions and they are equivalent. So keep in mind, identical and equivalent are not the same. So they are equivalent, but they are not identical. From the vector perspective, they have the same direction actually, but different sense. They point to opposite sense, or in general, we just call that direct opposite direction. And second, a direction and is multiple or identical. For example, the 1, 0, 0 direction is the same as 2, 0, 0 direction, because we can think of 2, 0, 0 is the 1, 0, 0 extend out of all the way to another unit cell. So within the unit cell, we have 1, 0, 0, but go out of that, extend to another unit cell, the long vector becomes 2, 0, 0. So we just forgot to reduce to the lowest integers. And number 3, several non-parallel directions with different indices are actually equivalent. So this is the family of directions. They are equivalent, but they are not identical. So equivalent means the spacing of atoms along each direction is the same. Furthermore, directions in cubic crystals are equivalent without regard to the order or sign. So this is another example we used earlier in the lecture. The 1, 2, 3 direction is equivalent to 2, 1, 3 direction, because if you pick that direction out, the atoms are the same on that direction. Sometimes it is necessary to refer to specific lattice planes of atoms within the crystal structure, or it may be of interest to know the crystallographic orientation of a plane or groups of planes in a crystal lattice. So the reason why do we need to describe or identify certain planes are a lot, but let's just name a few. For example, metals deform easily along planes of atoms that are most tightly packed together. We call those closed packed planes. So we need to name those closed packed planes and then to say along those planes the metals are deformed easily. Another example would be the surface energy of different phases of a crystal depends upon the particular crystallographic planes as well. So surface energy can be used in the application of materials. Therefore, we need to know or to name certain crystallographic planes within a crystal structure. To describe the crystallographic planes, again, we're going to use the Miller indices, a set of 3 integers. So mathematically, if we have a plane to describe the orientation of the plane in space, we use the normal line of the plane. So the normal line of the plane is a line that is perpendicular to the plane. So if we say this is the normal line of this plane is n, which now we see is pointing to the z direction. So this will be 1 j hat or 1 k hat, sorry, for example, 0 I hat plus 0 j hat plus 1 k hat. For example, this is the normal line of the plane. So we just use this 1 k hat to describe the location or orientation of the plane. Then we know this plane must be the xy plane or parallel to the xy plane. So here the same idea. The set of Miller indices we're looking for is the x, y, and z components of this normal, it's the normal line, not normal plane. I made a mistake here. So normal line of the plane, so which actually is a vector. So the algorithm here I'm presenting is to find the normal line of a plane. And in this case, we are talking about a lattice plane within the crystal. So step 1, if the plane passes through the selected origin, then we need to move the origin to another location, or we need to establish a new origin and set up a new coordinate system. Second, read off the values of intercepts of the plane with x, y, and z axis respectively, and those intercepts will be expressed in terms of the lattice parameter a, b, and c respectively. Number 3, take the reciprocals of the intercepts we got from step 2. Number 4, normalize reciprocals of intercepts by multiplying by the lattice parameters a, b, and c. So this step is similar to the step we're looking for the directions. Number 5, keep in mind that for crystallographic planes, we just need to clear the fractions, but do not reduce to smallest integer values. For directions, we need to reduce to smallest integer values. For example, if we have 2, 0, 0, we need to reduce it to 1, 0, 0. So it's the same line, but 2, 0, 0 is a line extend outside of a single unit cell. 1, 0, 0 is the part of the same line within the unit cell. But for planes, the 2, 0, 0 plane is not the same as the 1, 0, 0 plane. So we do not reduce to smallest integer values. And number 6, enclose the resulting Miller indices from step 5 in parentheses, just like this. There's no commas between those numbers. So for Miller indices of planes, we use HKL to representing the 3 integers, versus for lines or for directions, we use U, V, and W for the Miller indices of directions. Let's take a look at one example. So we're looking for the Miller indices of this diagonal plane. First step, we need to check the origin. So this is the origin now back here. The origin is not on the plane, therefore we don't have to move it or we don't have to relocate it. Step 2, we're looking for the intercepts of the plane with x, y, and z axis respectively. For x axis, the intercept is here at A. So x is A, and for y axis, it intercepts at B, so that's B. But this plane is parallel to the z axis, so if it's parallel, it never intercepts. Therefore, the intercept will be infinite. Step 3, take the reciprocals. X, 1 over A, y, 1 over b, and the reciprocal of the infinite c. So here, we can just write 0 directly. Step 4, normalize by multiplying A to the x component, b to the y component, and c to the z component, assuming the lattice parameters are ABC here. So after normalizing, we have 1, 1, 0. Next step, if we have fractions, we need to clear the fractions. But clearly we do not have any fractions, so it will be the same value as step 4. And we're going to enclose all the values in a pair of parentheses, but do not have commas between the values. So typically, if I'm going to work on this problem, I will set up a table and put the steps in each row. Example 2, this is a very similar problem. So we have a plane which is parallel to the YZ plane. In other words, it's parallel to both the Y axis and the Z axis. So first, check the origin. The origin is not on the plane, so we don't have to move it. Second, take the intercepts of the plane with X, Y, and Z axis. So the intercept with the x-axis is in the middle of this edge, therefore is a over 2. Since it's parallel to the y-axis, so the intercepts will be infinite. So here again, I don't think it's we need to put infinite times b because it's infinite, just infinite. And it's parallel to the z-axis, therefore it's infinite as well. Take the reciprocals. X component 2 over a, y component 0, z component 0. Step 4, we're going to multiply by a, b, and c separately. And here is the answer. Multiply by a, multiply by b, and c. Step 5, we're going to remove the fractions if we have any. If not, then we just leave it. And again, do not reduce to smallest integers for planes. And we have the Miller indices for this given crystallographic plane, which is the 2, 0, 0 plane. example number 3. For this example, if we are going to use the given coordinate system, this is the origin. But seems like this plane passes through the origin, so we have to move the origin to a new location, so it's not located on the plane anymore. So one choice, there are different choices. You can move it over here or move it over there. As long as the point is no longer located on the plane, you should have the same results. So now in this case, I'm going to move the new origin to the top corner, showing in this green. The green dot is the new origin. So here now will be my new x-axis. I call it x prime. And here is the new y-axis, y prime. Step 1, right? We move the origin to the green dot. And then find the intercepts. First of all, the plane is parallel to the x prime axis, so the intercept will be infinite. And the intercepts with the y-axis is here, which is the lattice parameter along the y-axis is b. The value is b. For the z-axis, the intercept section is over here. Is in the below the origin, so it's a negative z. Okay, and then next we're gonna take the reciprocals. Infinite, well, reciprocal of infinite is 0, and for the y component 1 over b. For the z component is negative 1 over c. Step 4, I'm going to normalize by multiplying a, b, and c respectively. So the answer will be 0, 1, and negative 1. Step 5 is to clear fractions if we have any, but again we do not. The last step is to enclose the 3 integers in a pair of parentheses. For the negative numbers, we need to put a negative sign on top instead of putting the negative sign in front of the number. Problem number 4, this is the easier one. Again, we check, do we need to move or relocate origin? No, there's no need to do that. And then second step, to find the intercepts with the x, y, and z axis respectively. So those points, assuming they are not in the middle, we should have numbers given, but it's not. So this is in the middle of the edge. And for the y, it's b. For the c, it's 3 over 4c here. And then take the reciprocals. Multiply ABC to normalize the values. And now we have a fractional number for the z component. So we need to clear the fractions by multiplying by 3 to each component. So here's the result, 6, 3, and 4. Again, do not reduce to smallest number, even if you can do it. For this one, we cannot, and we don't need to. And then we enclose the indices in a pair of parentheses. For crystallographic planes, we also have family of planes. So all planes that are crystallographically equivalent are indicated by indices in this braces. We call this is the 1, 0, 0 family. So all of those combinations, 1, 0, 0 plane, 0, 1, 0 plane, 0, 0, 1 plane, negative 1, 0, 0, all of those planes belonging to the family of planes. And all of those planes have the same atomic packing, or the atomic arrangements on those planes are the same. Some common crystallographic planes. the surfaces of the unit cell belongs to the 1, 0, 0 family of planes. Now, for the plane with the same Miller indices, this refers to a set of planes that are parallel and with the same interplanar distance. So the distance between those planes are the same and they are parallel if the planes have the same Miller indices, but they are located in different unit cells within the lattice pattern or crystal structure. Another set of plane is the 1, 1, 0 plane, which passes through the face diagonal. And this is the 1, 1, 0 plane. Again, all the planes that pass through the face diagonal, for example, you can draw another one, belong to this 1, 1, 0 family of planes. Another common one is the body diagonal plane, which is the 1, 1, 1 plane. And we can draw again another one should be another direction, like this. This is also the 1, 1, 1 plane, but maybe there's a negative sign in one of the indices, but they belong to the 1, 1, 1 family of planes. So again, you can see with the same Miller indices, or planes with the same Miller indices are parallel planes with the same interplanar distances. Some notes on Miller indices for planes. Planes and their negatives are identical, but this is not true for directions. Planes and their multiples are not identical. That's why we shouldn't reduce the Miller indices to the smallest integers. But the directions and their multiples are identical. Certain groups of planes are equivalent, so we call them the family of planes. And in cubic system, a direction that has the same indices as a plane is perpendicular to that plane. So that means if we have the 1, 1, 1 plane, it will be perpendicular to the 1, 1, 1 direction. Again, we said this 1, 1, 1 is the normal direction or normal line of the plane. If it's the normal line, it's perpendicular to the plane.